through this code along lecture. I'm going to open up Jupyter Notebook now. So to begin, we're going to import NumPy as NP, and we're also going to be importing a library called Pandas, and Pandas is going to allow us to actually read in CSV files, which are comma-separated value files, and other file types like text files or tab-separated files, and so on. So we're going to be using Pandas a little bit, and we'll be showing you a quick look about a few various Pandas methods that are really useful in conjunction with Scikit Learn. So Pandas can actually read in files into what's known as a data frame object. And it does this through the command pd.read_CSV. And then we pass in the file path to the file. So we're going to be opening up underneath text files. There is an SMS spam collection.tsv file. And it's a TSV, meaning it's tab separated. So we're going to pass in one more parameter here, which is going to be \t, and that indicates a tab. Just telling Pandas and Python that this particular file isn't separated by commas for each column, but is separated by tabs. And then we're going to assign this to a variable called df. And then off of this variable, if you hit dot and then hit tab once it's been defined, so if you run that cell that actually defined df, you hit tab, you'll notice there's quite a few attributes and methods. We actually don't need to worry about too many of these, but the one we're going to see right now is called head, and this is going to show us the first 5 rows. So this is our actual data set, and we've seen this before. We have a label indicating if a text message is ham or spam, and then we have the actual text of the message, and then we have the length of the message, and then we have the punctuation. So how many actual pieces of punctuation does this message contain? We still don't know how to extract features from the text. So instead, we're just going to be using these direct numerical features, and then later on we'll realize and learn how to actually convert this text message, probably the most important feature here, into numerical information using text feature extraction. But for this lecture, we're going to be focusing on things that are already numbers in this data set in order to use them to actually perform a text classification machine learning model. Now, machine learning models usually require complete data. So one easy way to check if your data is missing anything is by taking this data frame object and then calling isNull. And if you just run isNull by itself, it returns back another data frame of booleans indicating true or false is a null or missing value. So what you can do is off of this, simply take the sum, and it's going to treat these falses as zeros, and if there's anything missing, it'll say it's true, that it is null, and then it'll treat that as a 1. So if you say isNull and then hold .sum, then if you ever see a 1 here, then you know there's a missing value. In this case, everything is 0, so we actually know we're not missing any data. Now, we can also check information about this data frame, like how many rows it has, by simply checking the length of this data frame, and it returns back that currently we have 5,572 rows. So we have 5,572 text messages, each of them labeled, as well as understanding their length and their basically how much punctuation this particular message has. Now what we're going to do is take a quick look at the ham and spam label columns, and the way you can access columns off a data frame is by calling the data frame and then in square braces passing in the name of the column. The name of the column is right here, it's in bold, so it's either label, message, length, or punct. So those are our column names. Let's go ahead and check in the label by passing it in as a string. So here I just grabbed the label column, and if I say .unique as a method, it's going to return back the actual unique values. So here I have 2 unique values, ham and spam, and then I can call off this same column .value_counts, and it will actually count how many of each unique values we have. So it looks like we have 4,825 ham text messages and 747 spam text messages. Now what we're going to attempt to do is try to build a very simple machine learning model that attempts to predict whether a message is ham or spam based solely on these 2 numerical features, the length of the message and the punctuation of the message. And we can actually visualize this. In fact, if you check out the notebook that goes along with this lecture, if you scroll down, we show some code that allows us to visualize ham versus spam and the actual punctuation or the length of the message. We can produce histograms for it. So don't worry too much about what this actual code does, because this isn't really a visualization course. If you are interested in what this code is doing, you can check out my other courses on that. But really here, we're just interested in this visualization. So I'm going to just copy and paste the code that's here and then explain what it's actually doing. So this is producing two histograms, one for the ham messages and then one for the spam messages. So right now what this is doing is it's looking at the length column and it's actually showing it on a logarithmic scale. And notice here that the actual distribution of ham text message length versus spam text message length is quite different. Spam text messages look to be longer in length than ham text messages. And intuitively, that actually makes sense. A lot of ham text messages or legitimate text messages are going to be short. They're just going to say things like, okay, or on my way, I'll see you there. While spam text messages typically are going to be quite longer because there's a lot more information to convey because there's more spam. So we can check it out here by actually seeing something like this, free entry in a 2-weekly competition, etc. Most likely, if it's a spam text message, it's going to be quite a bit longer. So notice this one is 155 versus these other ham ones tend to be a little shorter. That's not to say that ham or legitimate text messages can't be long as well, but the distribution of each of these is quite different. So that probably indicates this is a good numerical feature to provide to our machine learning model. It's still simplistic, and we're really just focusing on how to use the Scikit Learn syntax. So don't worry too much about this being the most robust machine learning model ever. Now, also what we're going to do is we're going to take a look at the punctuation column and see if it has maybe a similar behavior. So again, just coming from our notebook, I'm going to scroll down here and then copy the code. It's essentially the same thing, but now looking at the punctuation column on a logarithmic scale. And you see here, these are the two histograms for ham versus spam punctuation-wise. And here, there doesn't tend to be any distinct behavior. It looks like spam tends to have a little bit more relative to other ham messages. It tends to have a little more punctuation, but here the behavior is not as clear or distinct as it is here. So in general, we can say that it looks like spam tends to have a higher range of values. It looks like spam messages tend to be longer, and there's less of a range of overall values. They all tend to be pretty long, versus ham has quite a large range of length. So we're going to be attempting to use, again, these two numerical features along with the label. Again, we're really just focusing on Scikit Learn. Later on, we'll actually learn how to use this text message data. So what we're going to do here is learn how to actually conduct a machine learning model with Scikit Learn. So the first thing to do is to split the data into a training set and a test set. And the way we do this is we simply say from SKLearn dot model selection, and you should be able to tab autocomplete that. We're going to import train test split. And we've seen this before. And then we're going to call train test split, and we're going to pass in X and Y. But first, we need to define what X and Y actually are. So what we're going to do is we're going to say that X is our feature data and Y is our label. So for our feature data, we're going to say X is equal to df, and I'm going to use two sets of brackets here. I'm passing in a list of column names, and we'll be passing in the length column and the punctuation column. Again, note the use of double brackets. I'm passing in a list of columns, which is why I have two sets of brackets. And then we're going to pass in our label, which in this case, that column is just called label. So we have X feature data and Y label data. Then what we're going to do is pass that into train test split. And what I encourage you to do is if you do Shift Tab in Jupyter, you can see the docstring for train test split. And if you scroll down inside of this, eventually you see this nice example, and you can scroll down and essentially copy and paste this tuple that says xtrain, xtest, ytrain, and ytest. Because using tuple unpacking, we can see what is actually returned here. Train test split, as we mentioned previously in the other lectures, is going to return your X training set and your X test set, your Y labels for the training set, and your Y labels for the test set. And then it's up to you to decide what the test size should be. So we're going to say that 30% of our data is going to the test data set. And then the other thing you may want to do is set a random state, because this train test split happens randomly. So it's going to grab random rows. That way, in case your data is sorted, that won't affect the actual train test split. So if you want to be able to repeat this sort of randomness in the train test split, you can provide a random state and then choose an arbitrary integer value to pass in. The actual value itself is kind of meaningless. What matters is that you use the same value if you want to repeat this train test split. So we're going to pass in 42, and if you pass in 42, that means you'll get the same train test split that I do. If you pass in a different random state, that's fine, you just won't get the same split that I do. So I encourage you to follow along exactly and type in 42. Again, that's just the random state for the split. So we're going to run that, and now we can check out the shape of this data by simply saying xtrain shape. And notice here, xtrain is 3,900 rows and 2 columns. So the 2 columns there are length and punctuation. xtest, if we check out the shape of that, is 1,672 rows with 2 columns. So xtrain, that's going to be our training data for the features, the length and punctuation. xtest, that's going to be the test features. And remember, it's still length and punctuation, but it's only 30% of the data. And we can see ytest, and if you check out the shape of that, that's essentially the labels right now. So notice it's just 1672 because it's the labels that correspond with xtest. So ham, spam. And notice the index position is kept in memory. So that's just the index that corresponds with xtest. So if we delete that dot shape and look at xtest, notice that we have these index positions, and that's going to allow us to match up the ytest to the xtest. And notice how this is not in order because we randomly selected them using train test split. Okay, so we have our xtest, our ytest, our xtrain, and our ytrain. Now it's time to actually create and train a machine learning model. So I'm going to show you how to train multiple models, and hopefully you realize that the exact process is really similar regardless of what model you choose. So the general syntax is the following. You say from SKLearn, dot, and then the family of models. And if you hit tab here, you'll notice that there's a lot of options. Not all of these are families. The first one I'm going to show you is a logistic regression model. So we say sklearn.linear model, import, and we're going to say logistic regression. So that's step number 1, importing the model. Then it's time to create an instance of the model. We will say lr model is equal to, and then you create an instance of a logistic regression. And if you do shift tab here, you'll notice that you have a ton of different parameters that you can choose. Often the default values are actually quite good. If you want to learn more about how to actually edit these parameters, what things like C mean or what solvers to use, you can check out the Reading an Introduction to Statistical Learning. That's the book we previously mentioned, which goes into a lot more detail of the mathematics behind a lot of these parameters. But these are the sort of parameters you'd be editing after you test your model against the test data. So just for example, we could edit this particular solver. So if you scroll down here, there's a lot of explanations over what these actually do, these different parameters. So if you wanted to edit the solver, you would just scroll down here until you see solvers, and this shows you the different algorithms it uses, as well as what options you have. So you have this Newton option, LBFGS, etc. And then it actually even gives you advice. So for small data sets, liblinear is a good choice. For multi-class problems, these can handle multinomial loss, etc. So just to show you an example of how you would actually do this, you could just, for instance, choose a different solver like LBFGS, and then say, for this particular logistic regression, I want solver to be LBGFS. Once you've completed that step, it's time to actually fit the model to the training data. So you just take your model, call .fit, and then pass in your X training data and the labels that correspond with that data set. Notice that I'm not setting this equal to a variable. I'm simply just calling .fit. I don't need to actually set this equal to any variable. I'm just calling .fit on the training data. and then it will report back the actual model that was used along with all the parameters that was used. And now the model is ready to predict. So coming up in the next lecture, we're going to show you how to actually test the accuracy of the model against the test dataset. We'll see you there.